Welcome to Physics for You. I am Shuvrajyoti Khamaru. Now we will discuss about what happens when alternating voltage is applied through a capacitor. Let the capacitance of a capacitor is C, connected with an alternating source of voltage represented by V equal to V0 sine omega t, as I have taken previously in the previous cases also. So C is the capacitance of the capacitor, V is the voltage. In the previous session we have learned that the phase difference between the current and the voltage was 0 in the case of a resistor, pure resistor. In case of a pure inductor, the current was lagging behind the voltage by a phase angle pi by 2. Now see what will happen in the case of a capacitor. So we have taken this as the voltage, applied voltage. Let Q is the instantaneous charge stored in the capacitor, that is the charge stored at any time in the plate of the capacitor. Q. So what is the potential difference? What is the voltage across the capacitor at that time? It is V equal to Q by C. V equal to Q by C. This is the instantaneous EMF equation. So from this equation, Q equal to CV. Again, Q equal to C. V means from 1, V equal to V0 sine omega t. Omega the angular frequency, omega equal to 2 pi by t, t the time period. Now current I equal to dq dt, that is equal to, this is dq dt, equal to C V0 ddt of sine omega t. Now dq dt is the instantaneous current in the circuit. It is I equal to CV0 omega cos omega t. This is equal to I equal to V0 omega C cos omega t. Now see, it can be written as I equal to V0 by 1 by omega C. 1 by omega C. This is a cos omega t. What I have written? I am writing again. That is I equal to V0 by 1 by omega C cos omega t. Now see from the dimensional, this has the dimension of current, this has the dimension of voltage. So obviously this should have the dimension of resistance. Now it is written as V equal to 1 by Xc cos omega t. Where Xc is called the capacitive reactance. Xc equal to 1 by omega C is called the capacitive reactance. In case of inductive circuit, pure inductor, the inductive reactance was XL equal to omega L, and in this case it is Xc equal to 1 by omega C. Thus the current in the circuit is given by I0 cos omega t. This may be represented as sine omega t plus pi by t. In the second quadrant, sign is positive. So as evident from equation 1 and 2, look at here. The current is leading the voltage by a phase angle pi by 2. That is, voltage is lagging behind the current by a phase angle pi by 2. In case of inductor, pure inductor, the current was lagging behind the voltage by a phase angle pi by 2. Here it is leading by a phase angle pi by 2. So if you represent it by a phasor in this diagram, see what happened. Suppose this is the applied voltage. This is V0. Then current is given by that is equal to I0. That is I equal to I0 sine omega t plus pi by 2. And this is the voltage V equal to V0 sine omega t. Again, if we draw the phasor, see what happened. V is the V0 sine omega t. That is, suppose this angle is omega t, then this is the phasor for voltage. This is equal to V0 sine omega t. Now, current is leading the voltage by a phase angle pi by 2. That is I equal to I0 sine omega t plus pi by 2. So current is leading the voltage by a phase angle pi by 2. So this angle is pi by 2. And the whole angle is given by omega t plus pi by 2. And this is the phasor for I. And see, this is I equal to I0 sine omega t plus pi by 2. Plus pi by 2. This is sine omega t plus pi by 2. So, what is the summary? The capacitive reactance is Xc equal to 1 by omega c. See here the resistance, that is the capacitive reactance changes with omega. Again, in case of pure resistance it is constant, always constant in a circuit. And in case of a pure inductive circuit, it was XL equal to omega L. So it changes with omega, that is the frequency, angular frequency. Again, in case of capacitive circuit, it changes with frequency, reactance. And what about the phase relationship? What is the phase difference between the voltage and current? In a resistive circuit, there is no phase difference between the voltage and current. In a inductive circuit, the phase difference between the voltage and current is pi by 2. That is, the current was lagging behind the voltage by a phase angle pi by 2. In case of a capacitive circuit, current is leading the voltage by a phase angle pi by 2. And that's all about the three different components, that is L, C and R. In the next session, we will see about the series LCR circuit. So today, bye bye.